Bradford seminar. Today, I'm Denise Mausrell, professor in CPRE and in the Civil Environmental Engineering program, and I'm extremely delighted to welcome Professor Steve Davis from University of California, Irvine to Princeton today. He's unusual in that he had the distinction of being both a lawyer and a scientist. He has a JD degree from University of Virginia and a PhD from Stanford in geological environmental sciences. He's combined these two expertises in a wonderful way, conducting valuable policy-relevant and rigorous technical research on energy technology and policy, socioeconomic inertia and lock-in of environmental problems, and the complex interactions of energy systems, agriculture and climate change, and global ecology. He has an absolutely superb publication record with numerous interdisciplinary papers appearing in Science, Nature, and the various sub-nature journals, Nature Sustainability, Nature Energy, Nature Climate Change, and Nature Plants. Also in proceedings of the National Academy of Sciences and in the Journal of Geophysical Research. He's the recipient of the AGU McElwain Medal in 2018, the ESA Sustainability Science Award in 2017, and the Casarelli Prize from PNAS for a paper in 2015. Today he'll discuss some recent work focused on net zero emissions energy systems. Thank you, Steve. And for those of you in the back, there's a few seats up here. I really encourage someone to come forward and take it and squeeze into some of the spaces over there rather than standing in the back.
Yeah, I'm flattered to think that there are people that would stand to hear me, but please fill in the seats. Thank you for that lovely introduction, Denise, and I'm really happy to be here. So the work that I'm going to present today is really based on a review paper that we published in Science last year with the same title. And so some of it will be sort of background for some of you, and it'll be punctuated by a couple of studies that we've done on subtopics that relate to net zero emissions energy systems. So when we wrote this paper and we were working on it, the idea of an energy system that could deliver modern energy services without adding CO2 to the atmosphere, we thought was almost like science fiction. We were thinking very long term, thinking we were being very creative, but it's actually come in the recent years to be an explicit goal of a lot of jurisdictions, including countries in Europe, states like California and Hawaii. The idea of reaching a place where we can provide the energy services that we all depend on with a net zero, meaning we may still have residual emissions, but at least it'll be balanced, offset by uptake of CO2, is really the goal. And that's because, and this comes from the IPCC's last assessment report, hopefully some of you are familiar with this plot. It shows the relationship of cumulative CO2 emissions since the pre-industrial era on the x-axis versus the temperature anomaly from the pre-industrial. And so in the black, you see sort of the historical relationship. And then these different colored lines are different scenarios where we emit either more or less. But what you should take away from this is that there is a cone of uncertainty, but these are linear relationships. And this essentially tells us that every additional molecule of CO2 that goes into the atmosphere is another tiny tweak on the global thermostat, at least on human timescales. And this is why we need net zero emissions. We need to stop adding CO2 to the atmosphere if we want to stabilize the climate. And the problem is, and I've plotted this on the same x-axis, these are the proven reserves of fossil fuels around the world. For those of you that don't study fossil fuels, proven just means that right now, at current prices, these are economic to extract. This is not all the fossil resources that we have around the world. These are the ones we think we can make money on. And you can follow it up and see that according to this, we're at least in a position to get towards 4 degrees of warming, which is obviously a lot higher than we'd like. So I often describe to my students, this is a sort of a cookie jar problem. We have this cookie jar of very attractive fossil fuels that are there in the ground, ready to make money on, and we have to walk past it every day for the rest of human civilization and not dip our hands in. And that's a pretty big problem, challenge. The good news, of course, is that there are lots of ways already to reduce CO2 emissions, and perhaps to even very low levels. So in recent years, I'm sure I'm not telling anyone anything new, that solar panels have gotten remarkably cheap. Electric vehicles are increasing in their penetration. Wind is as affordable as ever. Hydro is increasing in a lot of parts of the world. These are all exciting opportunities to reduce our greenhouse gas and carbon emissions. But the question that motivates my talk today is, how do we get to a completely net zero system? And what are the pieces of that system that are going to be particularly difficult to avoid? And so when we think about that, there are really three groups of services that are going to be difficult. The first that I'll talk about today is long-distance transportation of freight or passengers, and in particular aviation. The second one that we think is going to be particularly difficult, and a lot of people don't think about, is industrial materials like cement and steel, and we'll talk more about that. And lastly, something that probably a lot of you have thought about is, how do we make a very reliable electricity system that doesn't have any CO2 emissions? And we'll get into that. So before I do that, a slight diversion is to say, some of you may think, well, the net zero is the end goal, but we can delay, right? We can wait to get to zero and just worry about decreasing the emissions now. And I think that what's really arguing against that is the fact that energy infrastructure tends to be very long-lived. And so if we wanted to hit a 1.5 or a 2 degree target, we're already building infrastructure now that's going to be a problem for that. And this is a paper that came out over the summer from my group, where we looked at all of the energy infrastructure around the world that emits CO2, and we estimated its age, and we then projected, if it operates over its historical lifetime, how much CO2 will come from these already constructed devices. So pretend we never build another gasoline-burning car or another coal-burning power plant, but all the ones out there operate over their historical life. And what you're seeing here is what annual emissions would be over time into the future if just these existing things operated as they have historically. And the punchline of this study was that we have about 650 billion tons of CO2 effectively locked in, and if you include proposed power plants, it's actually up to 830 gigatons. And these colorful areas show you the different sectors related to that, or the regions in the right. And just to plot that on a graph that shows the budgets that we have to meet a 1.5 or a 2 degree target, the red dots show you the historical lifetime of power and industrial infrastructure and its historical utilization rate. And you can see that existing infrastructure on the left here is above the 1.5 degree budget already. And if you include the proposed infrastructure, we're getting towards the 2 degree budget. So all of this is by way of saying that the net zero emissions energy system isn't some far distance goal. We need to be working on this right now. Okay. So how much of this difficult stuff are we talking about first of all? This pie chart shows you, as of 2014, global fossil fuel and industrial emissions, which were about 34 billion tons in that year. And the exploded out sections of this pie chart are the ones that I'm going to argue are the especially difficult to avoid ones that we need to be paying more attention to. And so you can see on here the structural materials that we'll talk about. Up in the orange is the long distance transportation and aviation. And then this piece of the red here is the part of the power sector that right now at least is load following. So it's not sort of the base load, it's having to go up and down according to demand. And in total, this is more than 9 billion tons of CO2 emissions in that year, around a quarter of global emissions in recent years. And this is another important point. These difficult sectors are not just a few percent, they're a big chunk of the pie. So between the inertia in our infrastructure and the fact that this is not a small piece of the global pie, this is all, I think, motivating us to get going on figuring out some solutions to these difficult pieces now. So let's start by talking about the transportation. So fundamentally, the issue here is energy density. And so this is probably a review for a lot of you, but different energy sources have different energy densities in terms of their gravimetric, their mass. So dry wood has about 17 megajoules for a kilogram. Bituminous coal is up into the 20 megajoules per kilogram. And refined oil products are into the 40s. So this should explain a lot about why we don't have wood-fired cars, right? We like being able to fill our tank with something that we can drive 300-400 miles at a go. Anyone know what the energy density of lithium-ion batteries is in the same scale? Any guesses? No? It's less than 1. So maybe we could do wood-fired cars. But so lithium-ion batteries are a tough one for that reason, and not for the light-duty transport, as we'll talk about. I think that's something that we're already seeing is manageable, but the long distances and certainly things like aviation, it's going to be hard. We can also think about energy density in terms of volume. Hydrogen looks great from a unit of energy per mass, but it's very low when you look at the volumetric energy density because it's a gas. In contrast, jet fuel is more than 3,000 times more energy dense on units of volume. This is hopefully starting to give you some sense why flying a jetliner like this across an ocean is going to be really difficult to do with batteries or even with something like hydrogen. The energy density of that jet fuel really enables us to get this big old thing in the air for hours and hours on end. Similarly, some people are looking at hydrogen and things like that for transporting goods across the ocean on these sort of marine-going ships, but that's going to be probably a difficult thing in the near term to imagine doing without an energy-dense liquid fuel as well. And really, even these sort of Class 8 trucks that we're very familiar with, you can do a back of envelope to show that given current energy densities of lithium-ion batteries and the packing density of those that, say, is in a Tesla or a Chevy Bolt, if you wanted to maintain the current distance that these things can travel, which right now they get about 700 miles of range on a tank full of diesel fuel, the batteries themselves would take up about a third of the volume of the truck and maybe 40% of its payload capacity. You can start to think then 40% of the payload capacity, the economics of driving stuff around changes dramatically because you're hauling the batteries almost as much as you're hauling whatever you're trying to get. So it changes a little bit with hydrogen. You can imagine the issue with hydrogen is, again, its volumetric density, and so you have to compress it. High-pressure tanks, though, are reinforced and heavy, or they have cryogenic aspects that add to the mass, and so you still end up using a substantial chunk of the payload capacity or volume, even if you tried to do this with fuel cells. So what I'm trying to get at is that I think for the long-distance transportation and aviation, at least in the near term until some of you guys come up with brilliant solutions, I think we're going to need energy-dense liquid fuels to do these things. Now that's not to say it has to be fossil fuels. So I'm going to start building this schematic, and I'll do this for the rest of the talk, showing what I think maybe a net zero emissions energy system might look like. So we've got on here our demand for aviation and long-distance shipping, and I'm making a case that it needs to be some sort of probably liquid hydrocarbon, an energy-dense fuel. And our options that are known and well-known for doing that is possibly biofuels, or we could imagine synthesizing our own hydrocarbons. Now, if we wanted to synthesize our own hydrocarbons that weren't going to, on net, add CO2 to the atmosphere, what do we need? Well, first of all, we need to energize the process of creating those with something that doesn't emit CO2. So this area of these green down here are different options that we can conceive of for making electricity without CO2 emissions, at least directly. What else do we need? Well, we need the hydrogen. And if we're going to get that hydrogen without adding CO2 to the atmosphere, we're going to do it with probably electrolysis. And so we take some of that clean energy and we use it to split water to get the hydrogen. We also, though, need carbon, and that's the trick, right? We want this carbon to come from not a fossil source. So we're going to need to do something like industrial air capture of carbon from the atmosphere. The idea there is that if we take carbon from the atmosphere, synthesize a fuel, burn the fuel, and this is a net neutral situation in terms of carbon in the atmosphere. Of course, Some of the limitations here are the electrolysis in particular is not very affordable, and I'll say more about that in a second. Other options that are conceivable is we could use ammonia. So you can actually thermally decompose ammonia, and there are engines that operate on this, actually in the farm sector of the United States. So we know we can burn that, and because it doesn't have carbon in it, it doesn't release CO2. So it's not inconceivable that we would do ammonia for, say, internal combustion vehicles. But of course, to make that ammonia, we're going to need hydrogen, and again, we need that from a source that doesn't entail CO2, so probably electrolysis. I didn't say it, but hopefully some of you know, where do we get most of our hydrogen from now? It's not electrolysis, obviously, but does anyone know? Natural gas, that's right. So we steam methane reformation. We have an industrial process to manufacture large quantities of hydrogen, but it entails CO2 as you split that methane apart and drive the CO2 off. So that's not a good thing from the climate perspective, and that is about 1% of global energy goes into the steam methane reformation for making hydrogen. So it's not a small process currently that we would need to replace. Lastly, just for the sake of completeness, folks are looking at ways of making fuels directly, sort of artificial photosynthesis, although it seems like it's pretty far off in terms of the R&D at this point. So I mentioned that electrolysis is expensive. This is a plot showing the cost of hydrogen in these contours in dollars per kilogram as a function of the electricity cost and the capital cost of an electrolyzer. And I've drawn in red here the current cost of that methane-derived hydrogen, which is about $1.50 per kilogram. Right now, the cheapest electrolysis that we do is still pretty expensive. It puts us in this zone of, with kind of industrial cost electricity, the resulting hydrogen from that electrolysis is close to $5 a kilogram here in this red dot. So we really need to reduce this cost a lot, and probably one of the main ways is going to be making these electrolyzers cheaper. And so that, I think, is a research priority. So to summarize this first section, I've said that I think these high energy density liquid fuels are going to be necessary for at least some of our transportation in the near term, if not the medium and long term. And currently the options that we have, whether it's biofuels that maybe we're concerned about for other reasons of land use change or just the use of the land for those purposes, or it's the synthesis of our own hydrocarbons, which would entail that direct air capture plus the electrolysis. All of those are pretty expensive. You'd need a pretty substantial carbon tax to make them economic compared to fossil fuels now. But I do think making electrolysis cheaper is a big priority for this. So let's shift gears and move to the structural materials. A lot of you probably don't realize that a lot of CO2 comes from cement and steel making. In 2014, about 8% of the world's CO2 emissions was from cement alone, so 2.5 billion tons. And the process of making cement entails this reaction here called calcination. Essentially, we take limestone and we dump it in the top of a kiln, heat it up to 1300 degrees C, and that decomposes the limestone into the calcium oxide, which is the lime, the special sauce, if you will, of cement, and creates a lot of CO2 emissions. Now, to create these high temperatures, we also often use fossil fuels, but it turns out that the emissions to make cement are roughly half due to the fossil fuel energy inputs and half related to the process itself. So even if we're successful in decarbonizing our energy sector and we're able to electrify that heat input, we're still going to have to deal with these process emissions, which have nothing to do with fossil fuels. They're part and parcel of the way that we make cement now. A similar story applies to steel making. So it's a little bit less, about 6% of global CO2 comes from making iron and steel. And there are ways to recycle scrap steel without creating many new emissions. So you can electrify an electric arc furnaces and get steel that way. But we, lately at least, the Steel Alliance estimates only about 1/4 of total iron and steel emissions could be avoided by that kind of recycling. I think it's mostly about limits in how much scrap steel we have versus the demand for fresh steel. So where do the rest of our steel come from? Well, we have to reduce iron ore in these blast furnaces, and you can see on this, maybe you can, it's pretty small, that coke is used in this process. That's what reduces the iron ore, but coke being coal, it also creates CO2 as a byproduct, and so that's the process emission of CO2 from steel. So if we want to get these materials that literally hold up our infrastructure, if you look at a picture of New York City, you're looking at iron and steel. Really, we are going to need to think about a couple of different options. One would be carbon capture, right? So we could imagine, in particular people like the idea of doing this for cement kilns, capturing the CO2 that comes from that process and then presumably sequestering it out of the atmosphere. One of the problems is we have a lot of these cement kilns around the world. They're very hot, as I mentioned. They're leaky, they're not gas tight, and they rotate. So imagine kind of covering that up after the fact with a retrofit of carbon capture and storage is a pretty daunting engineering task. There's also the possibility, and I have it in the title here, of maybe coming up with alternative processes. So for example, in the steel making, it's possible to make steel without using coke as a reductant. You could use hydrogen, which I have on here at some point. Okay, yeah, the blue line is now connected to the cement and steel. So you could imagine coming up with alternative recipes for, say, cement and steel to get those products without using the same process. The other option, and that's what this plot is about, is that we could imagine using less of these things. And so, for example, there are people now interested in building fairly tall, multi-story buildings with timber alone. I don't know if you've been following this. It was in Nature a few months ago. One problem, though, is just looking retrospectively, it doesn't seem like we've decreased very much our use of these materials over time. That's what I have plotted here, is the tons of steel and cement per $1 million of GDP worldwide, and at least I don't see any clear trend there over these 15 years. It's pretty well flat. In developed countries, each of us uses about 1 kilogram of steel and cement per day. So obviously you're not buying 1 kilogram of cement every day, but somewhere in your life that's happening. So I think probably carbon capture and storage is going to be a big part of the solution if we're going to do this in the coming decades. And so I've added on my schematic here the geologic storage of that. I do want to mention another piece of work that we've done on cement. These are cement process emissions over time since 1930 worldwide. And these are in units of just carbon, so you'd have to multiply your 3.667 if you wanted to get to the CO2. But what we were interested in is not the process emissions themselves, but a reverse process that structural engineers have known about for a long time, but the carbon cycle community was not really paying much attention to, and that's something called carbonation. And so the picture you see here is actually sort of the end result of carbonation. This is why structural engineers know about it. As the cement carbonates, which is this reaction here, it absorbs water from the atmosphere and sucks up CO2 from the atmosphere to reform the calcium carbonate. It changes the pH of the cement itself, and it tends to lead to the oxidation of reinforcing metals like this. So it's a bad thing from the perspective of a structural engineer who wants the bridge to stay up as long as possible. But what we were interested in is, hey, this is sucking up CO2 from the atmosphere. How much of that is going on worldwide, and how important of a process is that? And so we modeled this with a very simple diffusion model where we have the depth of carbonation into a cement surface, a function of the square root of its service life, and different rate coefficients, which depend on the moisture in the environment, whether it's indoors or outdoors, whether it's been painted, the original lime content of the cement, and so on. And so just for an example, you can imagine that some cement structure is demolished and it begins to absorb CO2 over time. Whether it's left out in the open, it is going to absorb more CO2 than if it's, say, buried in a landfill. And I think that probably makes a lot of sense. So what we did was estimate, based on all of the cement that's been used over this time period, and some experiments that we did, some measurements that we did, and a lot of drawing from the literature, the rate factors for 26 different rates. And we set up a probabilistic model that estimated what has global carbonation been of all these cement materials since 1930. And so this is the same plot I showed you of process emissions. These are our estimates of uptake over time. And so the net, you can see, is actually substantially less than what those process emissions have been, such that in recent years, about 45% of the process emissions, we think, are being reabsorbed by carbonating cements around the world. So all of this is to say that, yes, we do have CO2, as I've told you, from the cement industry, and that's a big issue. This kind of suggests that maybe we should be focusing more on the fossil side of it, because at least over decades, the CO2 is going to suck back out some of that CO2. Just to mention that a lot of this is actually in mortars, which is something that's often used to surface buildings. It makes sense that it would be exposed to the air, and it has a high lime content. It's a little tidbit for your next cocktail party. So takeaways about industrial materials. I think alternative processes should be top of research agendas everywhere, but probably CCS is going to be necessary. I do think, based on this last study I showed you, that we should be prioritizing reduction of fossil emissions over the cement, at least. But we could also start thinking about how to dispose of and recycle cement materials so that we can enhance this carbonation process and get that CO2 back out of the atmosphere. Lastly, I think it's interesting to think that if we did put CCS on a cement kiln, then the carbonation process is going to be a source of negative emissions, which is something that might be very valuable going forward. All right, so last but certainly not least, and I've tried to leave myself time to get into this, I want to talk about electricity. So up here we're going to add a hospital as our indicator for a highly reliable electricity demand. And I think that this is something that what a lot of you are aware of and interested in is how do we manage to get a very reliable source of electricity from resources that are variable and at times uncertain, like solar and wind. So I'm going to talk about an analysis that we did. These are, sorry, my over-the-top animations. So one thing we can think about is energy storage, right? So as I have in my changed title here, the way that we're going to do this is by some combination of flexible generation or dispatchable generation or firm generation, if Jesse Jenkins is in the room. Demand management, so maybe we settle for having less power at certain times, or we're able to do without. And energy storage. So that's how we're going to make the budget of supply and demand of electricity work. So what I've boxed here are potential sources of carbon-free electricity that are, in some sense, dispatchable. And so we know that solar and wind down here are really attractive. As I mentioned at the outset, they're increasingly affordable. Probably the one that almost anyone you ask is okay with the idea of building a lot of that. And so that's great, but they are variable, and so we're going to need some of these other things perhaps to make ourselves fully reliable. We did a study that tried to look at this in what I think is a fairly transparent way, and our focus was looking at the continental United States and asking ourselves, just based on the geophysics of how much sunlight and how much wind is there in the United States, what sort of balancing are we going to need? How big are the gaps if we tried to go as far as we could with solar and wind that are going to need to be filled by some other flexible generation or demand management or storage? So what you're looking at here is the results of some of our analysis of 36 years of reanalysis data over the continental United States, normalized by the mean, the variability over the course of years of wind in purple, solar in yellow, and comparing that to a single year of demand in orange. And so what you can kind of see, hopefully you understand that we tend to get more sun in the summertime in North America here. But fortunately for us, the wind actually peaks in the wintertime, so that's a nice complementarity that we have. The question, of course, as I said, though, is what about moment to moment, hour to hour? And you can see, at least in the case of wind, there's huge variability over the year. So what we did was build a hypothetical power system where we said to ourselves, okay, we're going to build exactly the amount of solar and wind that we need to generate the electricity consumed in a given year. So in the space of 1 year, the solar panels and wind turbines that we hypothetically built generate exactly the amount of electricity that we need in that year, but not necessarily hour to hour, right? And that's what we call the 1x generation here. And so vertically in these plots I'm going to show you is the mix of solar and wind with 100% solar system at the top and 100% wind at the bottom, and all the mixes in between. Left to right, what we did was looked at the effect of spreading those generating resources out over larger areas of the United States. So you see, just for scale reference, something the size of DC at the left versus the entire continental United States at the right. And this is a system where like I said, we've built exactly enough to compensate us for the year, but we have no storage at all. What fraction of the time are we able to meet demand over that year? And so you see here that the percentages are in the order of 60 or 70%. Maybe if we integrated the entire nation, we're getting close to 80%. So right out of the gates, we find something interesting, I think, that a lot of studies have shown that it's feasible to get to about 80% of our energy from solar and wind, but that after that things get more expensive, that we then need to have more storage, more supplemental resources. That's falling out of our very simplistic analysis of just the resources themselves. I should have said that we assumed that there was perfect transmission lossless. So if you're in DC and the sun hits California, you can get those electrons for free without a single one being lost. That's obviously a ridiculous assumption, but it's going to bound our approach to see what's the best case, right, if we had the perfect grid. Now, what about if we add some storage? So this is still a system where we've built exactly whatever solar and wind we need to generate the annual consumption, but we've added 12 hours of mean demand's worth of storage. 12 hours of mean demand, by the way, is not a trivial matter. That's about 5.4 terawatt hours of energy storage, which is a huge amount. It's about 150 years of the Tesla Gigafactory's production. But what you can see is we get a lot more reliable. We're up into, at least if we integrate over the whole nation, into the 85-90% range. Interestingly here, if you look left to right in this first plot where there's no storage, which when we move left to right, we're basically considering the value of transmission, we cross a lot of contours. In the case of 12 hours of storage, not so many contours are being crossed. Effectively, what we're showing here is a trade-off that we can do better with a system with a lot of transmission or a lot of storage, but it might not actually be that valuable to try to do both. And that's a really important finding too, I think. Finally, I'll show you these bottom panels are where we've overbuilt effectively. We've added 50% more generation than we technically need if we looked at the annual output, because that may be the cheaper option than building a lot of storage, right? And you can see that overbuilding with no storage, we can still, if we integrate over the nation, get into the 90s. But in this final one where we've overbuilt and we've got 12 hours of storage, we're finally getting towards 99%, which 99% sounds terrific, but the requirement in the United States is for a 99.97% reliability. So you can have about 2 hours of outage per year, which is a very high standard to meet. So to dig in a little bit, I want to show first, left to right, these panels are showing you the benefits of storage. Within each panel, the left to right is showing you the benefits of the transmission system. And then top to bottom, we're seeing the benefits of overbuilding. So digging in a little bit more, this is now showing for all the 36 years we looked at and the months of the year, how reliable is this system. In this case, looking at a system that's 3/4 solar, 1/4 wind, and the 1 times generation with no storage. So all in all, over this time period, it's only 62% reliable. And just pulling out a week here from December in a recent year, you see all of that red hatched area is unmet demand, where even though the solar in yellow is coming in and out every day, the wind is lulled and it's not producing enough to compensate and to meet demand. Now, if we add, under the same system, we've now overbuilt and added storage. This is the 99% reliable system. It sounds great, 99, it sounds really nice. But that same week, you still see 5 days in a row here where a substantial amount of demand is still not being met. The green in these is now showing the charging of a battery, presume, or some storage technology during the day and discharging. But even still, we have this week-long period where there's a lot of electricity demand not being met. And so I think this is starting to unpack why a very heavily solar or wind scenario is still going to be difficult, because even though we're at 99% reliability, this is an awful lot of power outage over a 5-day period that people are not going to tolerate. That's the gap that we're going to have to fill. So we've looked at, as you move on these logarithmically towards the most reliable system, what sort of overbuild ratio do you need, and in the colored lines, how much storage might you need to get to sort of 99% reliability. And you can see in a 100% solar world, you might need 4 days of energy storage and double the size of your system. In 100% wind, you might need 12 hours of energy storage and 4 times the generation. So all of this is to say that as we go towards the 100% mark of reliability, trying to do that with just solar and wind becomes exponentially more difficult. So this is all to say that the geophysical variability alone, before you really get into the complexities of a sophisticated dispatch model, explain why meeting more than 80% of electricity demand with just solar and wind may be very costly. At big scales, continental scales, the gaps in the power production that we see are still long. Remember that week I showed you, and large, so thousands of gigawatt hours over several days. And that's something that's a challenge to do if you want to try to do that with just storage. So probably this is where some sort of non-emitting dispatchable asset is going to be very valuable. And finally, I mentioned that it appears like it could be wasteful to try to pursue both integration of large areas with transmission and large-scale energy storage. And I think this is really interesting because it sort of suggests that we might want to choose our horse early, whether we go with a wind-heavy system and build a transmission grid to support it, or we go with more of a solar-heavy system and don't worry so much about large-scale, long-distance, high-voltage transmission. So because these gaps that I mentioned in the 99% reliable scenario, for example, are nonetheless large, you can infer that anything that backs that up is also going to be used rarely. So if you have a system that's 99% reliable, anything that you build to back up that system is going to be necessarily only operating 1% of the time. And any capital-intensive resource that you only operate 1% of the time is not going to make a lot of economic sense. So what we really need, if we want to have some sort of flexible backup, whether it's storage or generation, is something with low fixed costs. And so that's a lot like the natural gas that we use now, peakers, for example, to back up our electricity system, where the variable costs are high, but the fixed costs are low. We're okay with the variable cost being high because we're not operating it very often, that 1% of the year. But we don't have to pay for it the 99% of the time that we're not using it. In the terms of the storage, the way this plays out is in how often are you cycling that storage technology over a year. If you're cycling something every day, then the capital expenditures associated with that are at their low point. That's why these curves all swoop up to the left. As you more rarely cycle those storage technologies, the prices rise, such that even in an aspirational scenario like the lithium-ion target here, which is $100 per kilowatt hour, we still see that if you're not using that more than a weekly basis, you're going to end up with some very high costs of the electricity that you're discharging. One of the most promising is hydrogen. If we could do electrolytic hydrogen for $1.50 a kilogram, which is the red dashed line, we see that we can actually get to the point where we only have to cycle that a few times a year to stay in a reasonable range of costs. So that's another reason that I think electrolysis should be a focus of our R&D. So the other piece of this, and I'll bring up my grand picture here now fully built out, is that if low capacity factors are involved, so we're trying to build backup resources that would help us for that 1% of the time, it may be critical to think about how we can integrate different energy services. So for example, if we build something that only backs up the grid 1% of the time, but the other 99% of the time can be being used to make some other product, then of course it can be higher capital costs. And so we could imagine coming up with technologies that would help us out for both the power side and, say, the transportation side. And one of the examples of that is if we need, say, these hydrocarbons and we're trying to synthesize those with electrolytic hydrogen, maybe we have power plants and electrolyzers that are operating most of the time to make hydrogen for the transportation sector. But when the wind goes down and we need some electricity, they can divert some of that hydrogen to either stationary fuel cells or even combustion turbines that burn hydrogen to back up the power grid without emitting CO2. So this is an example of how we could imagine integrating the energy system in ways that it currently is not integrated to overcome some of these challenges without necessarily having a lot of new technologies. So just to summarize, and then I'll have some time for questions, I've sort of made a case here based on the physical and techno-economic characteristics that net zero emissions energy systems are going to be particularly challenging for these three pieces of long distance transportation, the industrial materials, and the very reliable electricity beyond sort of 80% renewables. In terms of the energy dense liquid fuels, I think biofuels are on the table. And something my group's interested in is perhaps even using something like seaweed that doesn't require land or water inputs to make biofuels for these sectors. Synthesized hydrocarbons are something that we should consider if we have renewable hydrogen and CO2 that we captured from the atmosphere or perhaps got from a plant. Right now our best back of envelope is that a carbon tax would have to be on the order of $300 or $400 a ton of CO2 to get to the price of parity with fossil fuel gasoline. So we need to get cheaper on our electrolysis and probably the direct air capture as well. Ammonia is something I think it should be on the research agenda. It might have some interesting opportunities, although sort of the safety issues that, of large-scale ammonia production might be a factor. And then direct solar fuels I think are an exciting option, but we have a long way to go. And finally, the reliable electricity and the power sector. I think doing that with a large share of variable uncertain renewables, we are going to need some large quantities of storage and or flexible generators that have low fixed costs or, as we mentioned, alternate products. And so the hydrogen, CCS, all of these technologies could be really vital for that. So that's all I had for you today.
Thanks for that great talk.
Sure, thanks.
And we have 15 minutes for questions.
Very quick question. I'm KK from Department of Civil and Environment Engineering. And a quick question about when you model the solar and wind potential. The demand is status quo, or you consider about future electricity?
No, it was from 2015, so a single year. Yeah, it's a great question. How sensitive is that reliability to demand? It's something we're looking into now. It actually seems like it's not terribly sensitive in most of the cases we've done with idealized demand curves and all sort of sinusoidal shapes. It doesn't really make a lot of difference in the hour-to-hour reliability, believe it or not.
But how about if there's more electric vehicle, like charging equation?
Yeah, you're exactly right. I mean, what you really are interested in is sort of decorrelating your resources and having those combined resources as closely correlated to whatever the demand shape is. But what I was suggesting is we've looked at some different shapes. Actually, we've done that analysis now for the entire world, all the different countries, because we were interested in, different parts of the world have different resources and different geographic size to work with. And so we wanted to see how that played out. And there are different optimal mixes of solar and wind, but when we messed around with the demand curve, surprisingly, it was relatively insensitive. Yeah. Thanks for the question.
I'm wondering why you didn't include nuclear in your analysis.
In the final analysis, or?
On the grand scope of...
Oh, it's in there. It's on my little schematic, at least. Maybe you missed it. See the... Yeah, I didn't talk about it, although it was in my head when I was talking about integrating different parts of the power sector. You could imagine, because nuclear plants are capital intensive and like to operate as much as possible, you could use those, for example, to make the hydrogen and then have that hydrogen available to either put back into a generating technology or just divert the output of the nuclear plant directly to the power sector when you need it. I think it's on the table. It's just a matter of economics right now and social acceptability. Yeah.
Does your analysis make the distinction between free energy and heat? Because the available work is the key issue. And if the energy of coal and burning 1/3 becomes work, is that point built into your analysis?
In which part of we do consider energy efficiencies in the conversion process, but most of what I talked about today was mostly looking at the prospect of renewable energy, so there wasn't a lot of that baked in. We did have sort of current levels of efficiency of converting sunlight into electricity with panels or wind, but we didn't have coal and the thermal conversion efficiency as part of that. It's definitely something that we consider if we're dealing with coal or any fossil fuel, sure. Yeah.
Thanks for the talk. I'm curious, is there a scenario where we're still striving for net zero economy-wide emissions, but we accept that some of these harder sectors might have net positive emissions, but we still do things like direct air capture just without worrying about electrolysis and that kind of stuff? Is there a scenario where that's actually cheaper from an economic, like financial or energy basis?
Yeah, and we haven't actually analyzed that, but I think it's conceivable that there are going to be things that it's cheaper to just remove CO2 from the atmosphere than it is to fully decarbonize the process. For example, like I said, if it's $300 or $400 a ton of carbon to get a carbon neutral synthesized fuel, there's plenty of people that could tell you they could remove carbon from the atmosphere for cheaper than that. So you could imagine doing that. Of course, then you have to worry about what are you doing with that carbon. If you're going to sequester it underground or something, that you run into potentially issues of people not being happy about that. So, but yeah, I think it's a good point. You could imagine solving a lot of the difficult stuff with direct air capture in theory. Yeah.
Josh, I have a question. You've painted a really comprehensive picture here, which is inspiring. And yet you started by pointing out that not only do we have this huge CO2 emission now, but we have plans for increasing our fossil combustion systems.
Mm-hmm.
Have you thought about the transition from where we are, or may become in the next 5 years, to a system like this, and what you see as the real opportunities to move quickly and where you see the sticking points to be?
Yeah, most of my thinking around those sticking points is regarding the capital-intensive infrastructure that we build, sort of like that committed emissions analysis, sort of lock us in. And so the cement kilns, for example, and the furnaces that make the iron ore or reduce the iron ore are an example of where there's a tremendous amount of this infrastructure that's going to be hard to retrofit or walk away from. I haven't done really any pathways analysis. I leave that to the integrated assessment modelers. And there's some interesting work on residual fossil fuel emissions that's along the same lines of what are the most difficult things and how much of those are there, even in some of the very low emitting scenarios. But yeah, it's a great question of how do we get there.
Because what I'm thinking is that you're committed, the difficult sectors that you described are about 20% of the total. So we have 80%. Based on your analysis, it should be quite feasible to shift. And then the question is, how do we do that shift?
Yeah.
Which I think is an important
I mean, my hope
Yeah.
is that 80% is underway to some extent already, you know, with different degrees of success in different places, but that the sort of path forward is clear on electrifying most of our light-duty transit and using a lot of these cheap renewable sources of electricity. So the issue for me, and that's what I tried to sort of map out, is that 20%, we can't wait until we get 80% of the way to start it. We need to be starting it now. So, yeah.
So building wind and solar to more than capacity, how practical is that? Does it mean having solar panels everywhere in the...
No, it doesn't take necessarily that much land. That's not the big constraint.
So we could go beyond 50% over capacity? We could go to
Yeah.
4?
So if you think about it, even now with a dispatchable fossil system that we pretty well feel expert with, we still overbuild by, say, 20%. So the idea of being at 150% with wind and solar doesn't seem far-fetched to me. Yeah. Yeah.
Do you consider the future electricity generation in the system? So if we use the future generation, we have to use energy storage.
Yeah, so I think I mentioned that when I was talking about hydrogen as a storage technology, the idea that we would make a lot of hydrogen when we have electricity, and then whether it's a fuel cell or the people are interested in whether you could just combust the hydrogen directly in a gas turbine, that's an option. And it effectively is a storage technology in that way. Yeah. Sure.
I think you started off by saying that wood is 17 times more concentrated in energy than lithium batteries.
Yeah, that's right.
I could have, I mean, if you could convert wood straight in, I mean, it's ridiculous, but I mean, you could actually have a car that has wood in it, and it was like the 17th of the batteries, and you could go 300 miles with
if you could extract that energy somehow, yeah. Yeah. You know, what's interesting, if you want to think about the energy density, I find this useful, is when you burn a fossil fuel, you're taking the CO2, or sorry, the oxygen from the atmosphere, and you're then burning it, and then you send the exhaust CO2 out the tailpipe. So you're only holding some fraction of that energy reaction. In contrast, a lithium-ion battery is a closed cell. It has to hold all of its reactants and products. And so you're always going to be behind relative to a technology that can take from the environment and then dump into the environment, right? So, yeah, that's one of the fundamental challenges of the energy density problem with batteries.
Just a small one. So
Sure.
on Mark's question about over-generation, so am I right that there's a lot of overbuilding in places like Belgium? I think that there's a large amount of solar capacity and it's over. So it would have seemed to me that if that's the case, then we have a precedent for this kind of over-generation of renewables.
Yeah, I mean, I think there are places that have already super saturated in some sense with renewables. I didn't know about Belgium in particular, but in California you hear stories about negative electricity prices, and that's in part because we have probably more than we can use in those devices right now. So there is some precedent for that, and I think it's a known way because it's solar panels are cheap enough that they're far cheaper than batteries at this point. It's a way of making sure that we have the electricity when we want it. Yeah? Well, I didn't actually compare sort of apples to apples, the reliability difference when you build transmission and storage. I was more suggesting that strategically, it looks like it might not make sense to try to do both. So I'm not prepared to say that transmission is better than storage or vice versa, but it does seem like we might be wasting money to build a high voltage DC network that spans the continental US and then build a lot of storage. That may be a waste.
What role do you see for decentralized or distributed energy resources? Does that make sense at all? Should we continue doing that as an intermediate solution?
Yeah, that's a good question. I think I would probably not be very qualified. I haven't looked at those in detail. I think, in general, the thing that occurs to me is when you have more of something spread out, there's a loss of economy of scale. And so that's what I worry about with the distributed resources, although you are saving some transmission and distribution network costs, perhaps. So I don't have a great answer for you, but I think it's an interesting topic.
Does the transmission versus storage strategic clash or question hold across the world? Globally, so you sort of done that analysis globally. Are there any places where it's not so obvious that's an issue?
I'd have to look at the results that we've got from that global analysis. They're still relatively fresh, and I haven't studied them in detail, but that's an interesting thing to look at, is where do those not trade off, maybe. Obviously you can get to higher reliability if you do both. I showed that, but obviously we're not just concerned about reliability. There's a cost to consider there too. So some of the work we've done, that had no economics in it, but we've also now added some economic considerations to the model and optimizing for the mix of solar and wind and storage and other technologies to get the highest reliability for the lowest system cost.
Those choices might depend on where you are, I imagine, depending on what the local resources are like versus
Yeah,
the
absolutely.
demand.
That's right. That's right.
You might come to different decisions in different places
Yeah.
around the world.
That's right. So there's some places that just innately have more solar or not. Yeah, that's right.
How do you factor in the
Okay,
rapidly
let's
changing
get the-
demand response?
Can we get back to you? I was actually thinking if you would ask this question.
Yeah, so I think it's, at least in my circles, it's very well agreed upon that energy efficiency should be the very first thing we do in all cases, and it's going to be critical to head off the kind of growth that Denise was mentioning that's going to be happening worldwide. So I think that's part and parcel of anything that we talk about. I should have said it at the outset, probably. That said, the demand management piece, the sort of active management of the system to alleviate the reliability problems of a variable-based system, I think has limited options. It seems like at the sort of sub-daily scale, there are things you could do, but when you're talking about those sort of week-long periods that I showed where the wind isn't blowing, you're not going to shut down a lot of your demand. It would cost more to do that than it would to build, say, solar or in excess. Yeah, so people have evaluated the total energy available in way of demand management in different systems, like heating systems or cooling systems, things like that. And it's meaningful at the scale of hours to maybe even a day, but when you go beyond that, it starts to peter out, and you would have to start closing down big pieces of industrial infrastructure, and that would then cost a lot.
One more question, we have time for that. If not, just thank Professor Davis. Thank you so much.
Thank you. Appreciate it.